Professor for giving my very nice introductions. And thank you, Professor Surel Prasad sir, to provide me opportunity to be here and did my PhD work. So first, I will talk about outline. So this is all work. I'm going to present whatever I have done in my PhD. Now I'm working in the industry. So I will talk about introductions and motivations, then I will talk about four mechanisms which will take part for the plasmonic enhancement of the optoelectronic devices. And also I will talk about four work what I have done, and then I will conclude my talk. So let's talk about my introductions. Like again, I want to tell some about details. BSc I have completed here in Department of Physics in 2011. Then I did my master on the Agriculture in 2013, and until 2015, then doctoral degree was completed in 2023. I was postdoc for 6 to 7 months. Then I decided to switch to the industry. So I'm working in the R&D, background technology. So I'm working at the SDM product like high bandwidth memory. So again, that is the R&D. So we do experiments, and my research interest is plasmonics, photonics, and optoelectronic devices. I have hands-on experience in the semiconductor processing and photonics, optical simulation, and data synthesis. This is all about my introductions, and then let's talk about introduction of my presentations. So as we know, optoelectronic devices, they are being used basically photodetectors for different applications in our daily life, flare detection, pollution detection, also biomedical science and space science, also in the military and thermal imaging. So what is the photodetectors? Photodetector basically has the photoactive materials, and once it will be illuminated with the light, it will generate the excitons. And once you apply the bias across these photoactive materials, the exciton will be break down and it will move towards the opposite potentials, so that you can get the current. However, there are already there are some photodetector in the market, which is the silicon based and also gallium nitride based in the different wavelength. However, their fabrication is very complicated and they are not cost effective. Nowadays, lot of people are looking for the wearable photodetectors and sensors. So for having the better photodetectors and also cost effective, people are looking for the highly efficient, better speed and spectral selective photodetectors. Also, they should have flexibility and transparency for the wearable devices and also CMOS compatible devices. So here are some materials currently being searched and being used for the optoelectronic devices, like familiar 2D materials. So familiar 2D materials has graphenes, TMD materials, including the MOS2, WS2, also the black phosphorus, and Maxine. So what is the property, why they are being used? Because they have property to tune the band gap by changing the layer of these materials. So, and also they have property by changing the layer, we can change direct band gap to indirect band gap. Next, perovskite control dot. These materials also very photoactive materials which can generate the excitons, being used for optoelectronic devices like solar cells, photodetectors, also LED. And another material, earth evident materials like copper based chalcodonide. This is also photoactive materials and very stable in the environment. So by checking this property like thickness and elemental constituent dependent band gap tunability, making them potential candidate for optoelectronic devices. And however, if you use this material pristine, so their performance is not good because they have very low light matter interaction due to the very thin layer of the 2D materials. So in order to enhance the
this concentrate works itself, or you dope in some other material, then
this which kind of the work. Quantum dot will absorb the light.
And what is the size?
Nano level, like 10 to 12 nanometers. So okay, so plasmonic structure and metasurfaces. So what is the plasmonics? So plasmonics has two phenomena called surface plasmon polytrons and localized surface plasmon polytrons. So what is surface plasmon polytrons? Surface plasmon polytron is basically electromagnetic oscillation at the interface of the dielectric and metals. And once you solve the Maxwell equation with the appropriate boundary condition, you can get these dispersion relations. And by using the coupler, you can generate the surface plasmons at the different interface of the metal and dielectrics. It has property like surface plasmon polytron has property to confine in the small volume, and it can improve the light matter interaction. On the other hand, there is a phenomena called localized surface plasmon polytrons. So, once if you have nanostructures and illuminate with the light, it will generate the dipoles, and these dipoles will be oxidate, and it will re-radiate the same energy which is absorbed in the perpendicular direction of the oxidation of the dipoles. So this is called localized surface plasmon resonance, and the radiation mode vary with the structure of these nanoparticles. So, and another phenomena called plasmonic metasurface. So, what is the plasmonic metasurface? So, we have meta-atom. So, what is the meta-atom? So, it is like basically you design for the particular purpose. Like this is not the actual materials. Like just we have metal and you engineer the structure of these materials, like gold nanostructure, and it has a capability to tune the reflectivity, absorbance, also wavefront of the light, incoming light. Once you pass the light from this meta surface, outcoming light its wavefront can be changed, like polarization can be changed. This plasmonic and metasurface have capability to enhance the light matter interactions. So there are four mechanisms.
Engineered materials are stable, or what is this?
This is just gold, gold nanostructure. So you just engineer the structure like make the like a circle or something like a rectangular. So it is stable. So there are four mechanisms take place once you hybridise the plasmonics with the semiconductor. So first mechanism is called PIRET effect, which is plasmon induced resonance energy transfer. So if metal and semiconductor will come into the close contact and light will incident on this combination, dipole will be generated in the metals and excitons will be generated in the semiconductor. If their resonance frequency match very well, they will couple together and energy will be transferred from the one to another materials. So with the same phenomena, it's also depends on the how close contact is there. If metal and semiconductor like contact distance is more than 10 nanometer, so that there will be PIRT effect, means energy will be transferred from the metal to semiconductor. However, if distance between the metal and semiconductor is less than 10 nanometer, so that will be the FERT effect. So here energy will be extracted from the semiconductor to the metal. So that will be the quenching effect. I will discuss later in my next work. Another two effect is called PHET effect, plasmon induced hot electron transfer effect, and also plasmon induced charge transfer transition. So this is the plasmon induced hot electron transfer. Once light will be incident on the metal, it will generate the hot electron, and if energy of this hot electron is more than the Shakti barrier, it will jump to the semiconductor conduction band, and it will enhance the population of the charge carrier in the conduction band. Similarly, if you have the PICTT effect, light will be incident on the metals, so it will directly generate the charge carrier like electron in the conduction band of the semiconductor.
Why do you call this hot electron? What do you mean by hot?
Temperature to answer hot electron.
I think room temperature.
No.
Room temperature, why they will be called?
So like light is coming on like hot electron means like it is generating with the induced light. Without light, you can't generate that electron.
It is obvious.
If it absorbs
It is
light,
obvious.
then its kinetic energy will increase.
Yes.
So the proportional temperature will also increase.
That will be increased.
That's why it is known as hot.
Yeah. So okay. So here I am going to talk about four work. So let's see like how much time will be allowed. If time will not allow, I will just complete two work. In the first work, we have hybridized the plasmonic metasurface with the black phosphorus, and we have a graphene electrode on the top and bottom. And black phosphorus is sandwiched between them, and we achieve highest responsivity of this detector 495 milliampere per watt. And we published last in 2023 in Advanced Material Interfaces. Second work, we have extracted the graphene and gold nanocrystals and also perovskite vertically, and we have used the electrodes, and graphene here work as a charge carrier channel. So once light will illuminate and excitons will generate in the perovskite quantum dot, and it will move close to the graphene and will collect the current through the electrodes. In third work, we have a core cell structure. In the core we have metal, gold nanocrystals, and in the cell we have semiconductor. And then we spin coated at the graphene and light will incident. So this core gold will improve the charge carrier in the semiconductor. It will transfer the energy from absorbed energy from the metal to the semiconductor. It will improve the population of the excitons, and this excitons will be transferred to the graphene once we apply the bias. And fourth work, like we have MOS2 layer, monolayer MOS2, and we have pattern this nano disc. This diameter is 120 nanometer around, and again there will be increase the light matter interaction and it can enhance the performance of these photodetectors. So let's talk about one by one, like about my first work. This is about plasmonic metasurface integrated black phosphorus based infrared photodetectors. So here, why black phosphorus? So black phosphorus has property its atomic element in the different direction is different. In one direction it has zigzag orientation, and another direction it has armchair orientation. So, and the orientation of this black phosphorus can be recognized or characterized by using the polarization dependent Raman and polarization dependent PM. So, this material has optical anisotropy. So, in one direction it has highest optical absorption, in other direction it has lowest optical absorption. So, in that direction where we have highest optical absorption, we will get highest photoluminescence, and also this peak is very sensitive to the polarization. So you can see this is the polarization dependent Raman. So here in the armchair direction, you have highest intensity of this peak. So property of this black phosphorus is this is one layer and this is mass computable, and it has narrow band. Narrow band gap means like it has black phosphorus has property like if you have monolayer, its band gap is 2.0 electron volt. But if you have bulk, its band gap is 0.3 electron volt, which come in the mid-infrared region. Also, it has high carrier mobility, and which make them strong candidate for mid-infrared photodetectors.
However, layered material means the property grown by van der Waals interaction.
Like one layer atom attached with the other layer atom with the
Van der Waals.
वो वायु से
So, however, this layer are very thin, so it is have low optical absorption, which hinder their high appropriate electronic performance. So we need to intensify the light matter interaction to improve the performance of devices, which is made by the black phosphorus. So here we have designed the plasmonic metasurface. So how we design? So bulk black phosphorus has band edge in the mid-infrared region, which is the 3.7 micron. So we have designed this metasurface, which should have a valence in the mid-infrared region. So here you can see that we have done the parameters. radius, and here is the wavelength, and this is the reflectance intensity. So we wanted to have highest reflectance intensity. Okay. At a 3.7 micron. So here we have done the thickness of the gold parameter sheet like 50 nanometer, 100 nanometer. Also here the periodicity, and we have optimized the size of this disc and thickness and periodicity to have highest reflectance in the mid-infrared region. Here the electric field confinement.
So you are talking about plasmonic meta surfaces.
Yeah.
And you have deposited gold disc on a SiO2 substrate, right?
Yeah.
So how it acts like the meta surfaces? How you call it?
So meta surface is 2D array of the meta atom. So
It is not like metamaterial. Yeah, it acts like the metamaterial.
yeah, metamaterial and meta surface are both the same. But like metamaterial can't be like how to say a 2D array. You can have single boundary condition, and boundary condition can be different. But here
dimensionality which matters.
yeah. But this one has periodic boundary condition.
If this has the periodic boundary condition, from where we are just incident the light from top.
From the top. So here is the dipole generation. This is the XG graph plot. So you can see once light appears, light incidents. This is generating to different like the dipoles, like magnetic charge, and it is generating dipoles. And here is the again dipole behavior. You can see positive, negative, and then negative and positive. So here how we fabricate this device. We have done the photolithographic process. We fabricate the meta surface and dye transfer method to make the devices. Here is the SEM image of our meta surface, and this is our electrodes, and this is the meta surface. Here we compare the simulation and measurement.
What is thickness of the gold?
It was 100 nanometer. I think I have shown here. So
Gold thickness.
you can see here like 150 and 150. So highest is coming for the 100 nanometer.
Okay.
So 100 nanometer thickness. So here we successfully designed the meta surface, and by the simulation, and you can see like simulation and measurement resonance peak is matching very well. Next,
But they are quite far apart from each other. Their qualitative behavior can be taken to be the same,
yeah.
but as far as magnitude and this peak position is concerned, they are quite far.
Yeah, like because here we have done the normalization. Normalization, but in the simulation we can't do the normalization. So that's why. Yeah. So here is the we want to do the optical characterization of this black phosphorus transfer on the meta surface, and we want to compare like first this characterization we have done to check the orientation of this black phosphorus. Means by first we want to check our black phosphorus is okay or not. Like okay means how the peaks are matching well with the reported literature or not. So here we have seen that all the peaks same as the reported result in the literature. Here we have done Raman polarization dependent Raman, and we found that this orientation is the zigzag and this orientation is the armchair for this black phosphorus. Next, we have probed these two positions, basically here and here, and we have probed at two positions, and then maybe I can use the mouse. And so here we have measured the PL at the two different positions. We found that photoluminescence here is the very high, and once we hybridize, it is getting quenched, which is due to the dipole-dipole interaction and the plasmonics and excitons. Here, polarization dependent, here we have measured at two different positions. Here we observe that degree of polarization is reduced, which is due to the energy transfer from the semiconductor to the metal. Next, here is our device. We have done the dry transfer method, top electrode. This is the schematic, and this is our actual device. And then we have measured the IV, power dependent IV with the different bias, and we found that at the negative bias we have the highest photocurrent because we have asymmetric circuit barrier, because upper graphene has the contact with the air, but bottom graphene don't have contact with the air, so there is asymmetric circuit barrier. And also we have measured the fluorescence independent photocurrent, which is similar to the optoelectronics properties, which one we have already observed in the previous page.
So you have deposited graphene from which method? You by CVD
No,
or by spin coating?
This is dry transfer. So you have layer, scotch tape, then we transfer on the, like, how to say, this is layer. We have scotch tape, take it out, then transfer on the this.
You transferred the graphene on that surface.
Transfer in the optical microscope.
Okay.
Then here is the charge carrier transfer mechanism, how it will take place. Once this is the black phosphorus and this is the graphene, and once it will come in the close contact, it will form the Schottky barrier. And once we will apply the bias, charge will move to the different bias and we will get the photocurrent. Here is the we have done the photocurrent mapping at 3 different bias. This is the 0 bias where you are getting the current. You can see the photocurrent is generating inside the graphene, black phosphorus, and highest photocurrent you are getting for the negative bias. Next, here we have done transient response of this detector, right time and fall time. And response time of this photodetector we have in the order of the nanosecond. And here we compare this device without the plasmonic nanostructure hybridization. And here we able to see that all the figure of length, photocurrent, responsivity, and EQE is being enhanced by 4-fold. So here we have compared our result with the other of this work, and at that time our was better. So we were able to publish this work in Advanced Material Interfaces. And this is the conclusion. We successfully demonstrated highly sensitive to black phosphorus detectors by enabling the plasmonics enhancement by using the plasmonic beta surface.
It means the plasmonic behavior are due to the interference between the gold and the graphene. Black phosphorus, that is the scientific structure like that. How the photocurrent is going to be enhanced in this in your case?
Okay.
What is the mechanism behind that? How
So,
the electron is going to be transferred?
So once light will incident on the meta surface, it will confine around the edge of the disk. We have meta surface and meta surface has disk.
Okay.
Already I have shown the simulation that field is confining around the edge, and that field will be interact with the semiconductor. So that, and once it will interact, it will transfer energy from the metal to the semiconductor, and it will improve the population of the excitons in the black phosphorus semiconductor. So it will improve the optoelectronic performance.
Basically, role of matter surface is to increase the reflectance. Am I correct?
That is
Plus,
good calculation.
There is you want to avoid the reflection.
No, actually,
What is the role of matter surface?
That creates a local field.
local.
Local electric field. There is the creation of some local field due to which the plasmonic effect is just going on.
Local electric field is generating due to dipole generation.
Dipole, yes.
And that dipole will be accelerate once you have meta surface and dipole. So when it will be accelerate? So acceleration will happen like you are exciting with some energy. It will absorb energy and it will accelerate. And it will re-radiate the same energy, but it will be absorbed in the another direction. So that energy is called the reflectance. So we say that this is absorbing the light at a particular frequency and re-radiating. That is the reflectance. Re-radiation is called the reflectance. But it is absorbing the energy.
It's true.
Yeah.
I want to know the role of matter surface. What does it do?
So now I will talk about my second work, that is about enhancing responsivity of the Perovskite quantum dot graphene highly gate free photodetector, and we have controlled this response by morphologically controlled plasmonic gold nanocrystals. So why Perovskite quantum dot? So perovskite quantum dot is basically has high spectral selectivity, tunable absorption emission, and also significant absorption coefficient and exceptional quantum efficiency, and it has also low cost to solution processability. Which makes them excellent candidate for the Photodetector.
What is size of that quantum dot?
Okay, I'm going to talk about here. So here we have compared. This is the TM image. This is the scale bar, and we have seen like size 10 to 12 millimeter. So here is our schematic, and this is the zooming image. You can see like here we have the graphene and nanoparticles. Nanoparticle size is also in the nanometer order, like 27 nanometer, 45 nanometer, 50 nanometers. And here is the perovskite quantum dot. Here we have done the XRD and TM to characterize the synthesize the perovskite quantum dot, which tell that this quantum dot has the cubic structure. And
in case of perovskite quantum dot, which types of material you have used? You have made perovskite material.
Yeah.
What is the composition?
What is composition?
Composition is here. Like basically perovskite quantum dot has this kind of composition. So we have used MAPDBR3. MA stands for the methylene ammonium, MAPD, lead, and BR3 is like bromine. So we have used that formula. So here I have written MAPDBR3. So next, this is the nanoparticles we have synthesized by seed radiated method. And this is the spherical shape, you can see. This is the octahedral shape, and this is the octahedral shape. The size distribution we have plotted and calculated using near about like 27 nanometers and 45 and 50 nanometers. Next, we have calculated the scattering cross section of these nanoparticles and compare with the absorbance of the synthesized. So this scattering cross section is coming from the simulation, and this absorbance is coming from the measurement.
In the previous nanoparticle case, we have seen quite a uniform distribution, and then there is a heterogeneous distribution. So that's a macroscopic level understanding for this distribution.
Microscopic, yeah, like again, if you see this distribution, but like for the large area, it will not that much uniform. If you see, yeah, but for the particular area,
In a confined geometry, it will be
uniform. So here we can see like the simulated scattering cross section matching with the measurement, and so when we compare all these three kind of nanoparticles, we observe that this RD has the highest absorbance and the scattering cross section compared to the other two, because it has large number of the edges which take part to confine more light, which will have high scattering cross section and absorbance. So here the electrical confinement of all these particles.
You calculated scattering cross section, that is theoretical.
Theoretical. In the simulation. We have used the numerical ability to calculate this one. Next, we have measured the absorbance, luminescence, and this is TRPL for all 5 combinations. Like here you can see graphene, and we want to see how optical property is getting enhanced once we hybridise. And here we can see that after hybridization for the particular RD, we have highest optical absorbance compared to the other combination, because already we have seen in the previous page, RD had the strongest scattering cross section and absorbance. We can improve more like magnetic interaction. So here we are able to see highest optical absorbance, and also photoluminescence is the same like what is the absorbance. Here we have measured the TRPM, and we have how to say fit this plot by exponential plot. And here T1 is coming from the surface trap, state recombination, and T2 is coming. So T1 is called long, short lifetime of the excitons, and T2 is called long lifetime of the excitons, which is due to the surface trap state recombination, and also T2 is for the direct bind-to-bind recombination. So here we have calculated for all 3 combinations and found that for a particular combination we have get longer average lifetime of the excitons. So if you have large lifetime of the excitons, you can have high probability to extract the applied bias, and you can get more current compared to the other combination. So here is also we have measured atomic binding energy of the quantum bond without hybridization and with hybridization. Here we observed that once we hybridize nanoparticles with the perovskite quantum dot, binding energy is getting lower. So we found that it is coming from electron is hard electron is transferring from the metal to the this atom, and which is lowering down the atomic binding energy. Next, in order to understand the charge carrier transfer mechanism, we have drawn the energy band diagram. Here you can see that once light will incident, here three mechanisms will take place. One is the HET, hard electron transfer. Another one will take place like PICT effect, and this is the PRT effect. All three will take place, and it will synergetically enhance the population of the excitons in the semiconductor in the conduction band, and will improve the applied electronics performance. So this is the device fabrication techniques. We have CVT grown graphene, and we have done lithography to make the channel of the graphene. Here you can see that there is some dark line like inside compared to the color contrast you can see. So here is the graphene, and here is no graphene. So first we make the channel, and then again second round lithography we have done to make the electrodes, and we have done the spin coating to make the devices. And we have done the optoelectronics measurement, and we found that for the photocurrent for this particular combination we are able to see the highest. Then we focus on the highest one and the lowest one, and we compare all the responsivity, detectivity, also EQE, and this is the rise time and fall time. And also we compare all four combinations, and we have converted this figure of merit by using this formula, and we compare our result with the previous reported result at that time, and our was the best, so we were able to publish this work in the advanced optical materials. So okay, so let's talk about another work. If like, so this is the earth embedded materials.